Now we're going to look at, what is going on with what's called stratospheric ozone destruction, where some global observations, like how have we seen the ozone concentration go down, and what could be some of the causes of the destruction of ozone in the stratosphere. All right. So if we, one thing that is known for sure, if you look at, over time, watch the ozone concentrations, that there's a seasonal fluctuation across the world with the ozone concentration. And that makes sense, whether you're in the northern hemisphere or southern hemisphere, depending on the tilt of the Earth, because the production of ozone is really dependent on the presence of high energy UV photons. And if the UV intensity is less or more, depending on what time of the year you are, you're going to see these fluctuations with the amount of ozone that is produced, because the ozone production is dependent on the oxygen being split apart to give the free oxygen atom that is available to collide with the oxygen to give ozone. So the more ultraviolet energy is, you think the more driving force there is to create more ozone. And so we see these regular fluctuations, northern hemisphere versus southern hemisphere and whatnot, based on the amount of ultraviolet light that's available at any given time. But what's particularly disturbing and not readily explainable by the seasonal fluctuations is that the minimum ozone concentration in Dobson units over time in the Antarctic zone, the minimum has gone down. So even though we expect there to be a lower concentration of ozone in certain times of the year, due to the way the presence of the ultraviolet light versus the presence of some other chemicals that are seasonally fluctuating in the Antarctic and also in the Arctic zones. But this particular graph is just showing the Antarctic zone, and what it is the minimum ozone, and then the numbers here, 9-17, 9-15, is in this given year, in say 1979, the minimum ozone concentration occurred on this day in September, and it was 209 Dobson units. Then in 1980, the minimum was 10-15. It's around the same time, September, October region, but the minimum is decreasing. Okay, there's some variation, some fluctuation, but overall, over time, the minimum amount is decreasing. Okay, and so that is cause for alarm, and so we need to understand what kind of chemistry is going on in the stratosphere, because that's where most of the ozone is to begin with. What kind of chemistry is going on there that could cause the ozone concentration to go down? In other words, to disrupt the steady state cycle of ozone oxygen. Well, there's natural sources that will interfere in that Chapman cycle to pull out oxygen or ozone and disrupt that natural steady state reactions. And the two natural sources that have the biggest effect on the ozone concentration are water vapor, so that would be water molecules that have made it all the way up into the upper atmosphere, or nitric oxide. The water, as it turns out, most of the water that's evaporated from the oceans and lakes and whatnot precipitates back down. That's the water cycle. So most oxygen that gets into most water that gets into the atmosphere rains back down, if you will. But there is a very small amount of water vapor that does make it into the stratosphere. And when it gets into the stratosphere, remember the water molecule, if you do the Lewis structure for water, you'd see that oxygen, hydrogen, those bonds are strong, but they're not that strong. And so they can be broken by the high energy ultraviolet radiation that's in the stratosphere. They are broken. And when they break in the presence of the UV radiation, they form what's called a hydrogen free radical and a hydroxyl free radical. One electron goes with the hydrogen, the other electron goes with the OH, and you have these very reactive species. Only about 5 parts per million water make it into the stratosphere, but that little tiny bit can react with the ozone, and after a series of reactions, it can help to convert ozone into oxygen. I won't go through the chemistry, but the presence of water naturally that's naturally, obviously, in the atmosphere at relatively low concentrations can disrupt the Chapman cycle and pull ozone out of the Chapman cycle, serving to decrease the concentration of ozone in the stratosphere. The other natural process is the nitric oxide. Nitric oxide will react with the ozone to eventually, convert the ozone to oxygen as well. And the nitric oxide actually has natural sources from the nitrous oxide. Nitrous N2O, or dinitrogen oxide, is a natural chemical that's released by microorganisms in the soil as it's, as bacteria and other microorganisms, single cell organisms release N2O as a natural a byproduct of the chemistry of those types of organisms. That N2O is not very reactive. It can make its way up to the stratosphere, and once it's in the stratosphere, it can be converted to NO, and that NO then in turn will react with the O3 to give back oxygen. So it's a complicated system as well. And the other thing to note here is the nitric oxide can come from, I should put the arrow this way, come from the nitrous oxide. That's the natural source, from nitrous oxide to nitric oxide. Nitric oxide can also come from unnatural sources, combustion engines, and we talked about that a long time ago. It's just that normally the combustion engines are in the troposphere, and they don't, the nitric oxide that's produced, or nitrogen monoxide that's produced in the troposphere, doesn't normally make it all the way to the stratosphere because it's so reactive. But if you put a combustion engine up near the stratosphere, you can produce nitric oxide up there, and that does occur with supersonic jets that fly really high. Now, because of this pollution problem in the stratosphere, the United States opted not to build a fleet or have supersonic transport jets, and most European countries that were using those have stopped. They're just too expensive and not safe enough. It's not worth the hassle. So those are going out of service. But even if you factor in these natural sources of nitric oxide from the nitrous oxide and water, the hydroxyl free radical and the hydrogen free radical from water, it still cannot explain, when you factor in and do all of the modeling and the atmospheric chemical modeling, these natural sources cannot account for the 8% decrease, of ozone over the last 20 years. Okay? So there's got to be something else, probably man-made. 8% decrease. There's been a decrease, and these natural sources cannot account for it over the last 20 years. So there must be something else that has been put into the environment over the last 20 years that could disrupt the Chapman cycle and disrupt the natural steady-state concentration of ozone